This talk is devoted to optimization methods for open quantum systems driven by coherent and incoherent controls. This talk is prepared following to our joint work with Alexander Nikolaevich Pichin. Thank you very much for this excellent conference. Last year, I took part also in your conference, and I am glad to take part just now. Further, some introductory slides are devoted to this direction. I mean, quantum systems, quantum control, numerical optimization. And it can be also possibility to provide analytical computations also. Because the introductory slides have more text than I can read during this short time, I want to say that this detailed text is more for video record, which will be available on YouTube, because the organizing committee will upload this record. Okay, and that's why I very shortly will comment the following introductory slides. Okay. Quantum systems and quantum control. Quantum systems mean individual molecules, atoms, and so on. Quantum systems are defined by various quantum mechanical equations. For example, Schrödinger, Gurini-Kossakovsky, Sudarshan-Lindblad, and so on. Are classified to closed without interactions with environment, accepting possible dependence on coherent control, and can be open system also. And because in some research, closed system can be preferred to analyzing, then we can consider without some additional facts as a closed system. And at some case for idealization, for analyzing main properties, and so on. After that, quantum control. Quantum control can be via shaped to other paths. For example, I talk about coherent control here. Can be incoherent control via quantum measurements. It can be such type, and incoherent radiation can be also. Quantum control is for obtaining various desirable properties for quantum systems, for example, breaking a chemical bond in some molecule. Mathematically, quantum control is formulated using terms of quantum systems and the theory of optimal control, mathematical theory of optimal control, where abstract statements are considered. For you know the theory and the first and second order necessary optimality condition. I mean, Pontryagin maximum principle, Gabasov secondary order optimal necessary condition. Second order, and quantum control is important for developing quantum technologies. Some books, some surveys. This slide further. Shortly about optimization methods for quantum control, both for closed and open systems. We can talk about infinite dimensional optimization, and also we can talk about finite dimensional optimization. I mean that if we consider, for example, steeped dancing method, and so on, Krotov-Zhurabets model-to-Rinichi method. And then we provide sequential improvements. Also can be sequential approximations if we consider simple gradient method without adjusting the corresponding parameter or for each iteration. And I want to say that it is provided in the functional space of controls. And upon dragging maximum principle, we can solve the corresponding boundary value problem. Also, gradient, conditional gradient, projection gradient methods. These methods are based on the linearized version of dragging maximum principle. After that, we can narrow our search space, I mean, functional class of controls by considering piecewise constant controls instead of measurable piecewise continuous controls. Moreover, the statement can have piecewise constant controls from its initial point. I mean, maybe some another parameterized classes of controls, and various methods for optimizing these parameters can be used. For example, gradient and same pulse engineering for adjusting parameters for piecewise constant controls. BFGS also CREB, this some special class of controls with trigonometric functions. Node-limit method is used here, and various classes and various methods can be used for global classes, controls, and methods, various methods for global optimization. I mean, some, of course, not 100%, of course, some approximation for global solution, of course, using genetic algorithms, stochastic optimization via differential evolution, dual annealing methods, and so on. Also, it's interesting to consider this type of methods when we consider some generalization of the ordinary optimal control problem, and the generalized statement of the optimal control problem allows discontinuous solutions, impulsive controls, delta function, and after that we can approximate as a corresponding solution for the initial class of controls. And I want to say that there is the corresponding maximum principle, this book, and also our article was published as a generalization of the Krotov method for this type of optimal control problems. And after that, I will say you about a general statement of open and level open quantum system with simultaneous coherent and incoherent controls. This density, this matrix is density matrix with these properties, and V is coherent control and is incoherent control. Also, it's possible to consider Incoherent control also here via the lamp shift. And this formula represents the superoperator of this patient. This system is open. It's important to say that incoherent control is non-negative during all the time because of physical meaning of this control. For more details, you can consider this interesting article where fundamental results are given. After that, it was this article, interesting article, and two important points are mentioned by me just now for this article. I mean that approximate controllability, this property, and this property was studied and some method for approximate steering for the system was proposed, and this method is based on dividing our time range to two stages. The first stage uses the eigenvalue values of the target density matrix. Target density matrix, I mean such matrix for this matrix, we consider the following requirement at the end of the second stage. And the first stage considers some intermediate target density matrix, and the density, these density matrices have the same eigenvalues. And the first stage uses these eigenvalues for considering this simple incoherent control. Simple formula, simple computations, but excellent idea, of course, without some iterative optimization. This formula is due to analyzing properties of the system. And this stage is carried out under zero coherent control. And at the second stage, under zero incoherent control, we optimize coherent control for satisfying this property. Some final density matrices should be found and according to our requirements for accuracy. And we can adjust the final time here, of course, not only coherent control. Some important properties of this message. And after that, in these papers, I mean 26 to 27, 26 this article by Pechin and Rabbits, and 27 this article by Pechin. And in these articles, some examples for 2 and 4 level quantum systems were considered. And in the further articles, also 2 and 4 level open quantum systems were considered, and various statements of optimal control problems were analyzed, for example, steering problem, maximization of the Gilbert-Schmidt scalar product, and another objective functionals, and various classes of controls, coherent and incoherent controls, constraints, various constraints, various optimality conditions, Pendragon maximum principle, and so on. Numerical methods, various numerical methods for optimization, and various physical properties were analyzed. I will talk shortly about some such results. And the abstract for my talk contains more references, and last year some article published by us where we considered two qubit, I mean 4-level open quantum system with simultaneous coherent and incoherent controls, with the requirement to steer the system to some given target density matrix. But in this talk, I will further consider only 2-level case, 1-qubit case, following our articles. Okay, 1-qubit quantum system. It's some particular case for this general statement, and we have this density matrix and linear in control, incoherent control, Hamiltonian, and this dissipation superoperator, and these matrices are considered. For more details, you can see this paper. After that, it's very interesting and important to consider block parameterization, because this parameterization gives projection between density matrices and block vectors, and we consider this system whose states are block vectors considered in the block ball. This ball is unit ball whose center is the region of the three-dimensional real space. You see that this good simplification for analyzing quantum systems, optimal control problems for this system. Okay, and after that, for this 1-qubit system, we consider 2 examples of using the described above 2-stage method for approximating steering. For the first case, we see the initial point in the interior of the block ball, and the target point is on the block sphere. And the case B is with the initial point on the sphere, and the target point is inside the ball. And the blue part of this complex trajectory represents the first stage, incoherent stage, and the red part represents the second stage, coherent stage. After that, I want to say about various objective criteria. For example, minimization of the distance Gilbert-Schmidt distance for a fixed final time. And also we can consider this formulation when it's needed to minimize the final time and steer the system considering some target density metrics. In other words, it's the problem for generating a given target density metrics. In terms of the block parameterization, we consider this objective functional. It's needed to minimize this. And as this article considers, we can formulate some series of optimal control problems with fixed final times and solve these optimal control problems and adjust the final time according to this requirement and this, of course, terminal condition. After that, maximization of the Gilbert-Schmidt scalar product. This paper was published by us, and in other words, mean value, and also we can consider the problem with non-fixed final time, where it's needed to minimize this final time and maximize this mean. After that, according to this article, Ullman and Jones fidelity and minimization of T. This article was selected by the publisher for its describing on the rubric of highlights. And the describing article is bringing quantum computer a step closer, this link. And the publisher recently has made this open access for our article, this link. And after that, I want to say about various classes of control, various constraints. We can consider, as I said, measurable, piecewise continuous, piecewise constants, and other classes of controls. We can use various constraints of controls. For example, for piecewise controls, we can restrict amplitudes and variations. And it's important from physical point of view and mathematical, from computational point of view. It's very interesting to analyze structures of optimized control processes. Some example from our article. It's needed to maximize this mean and Gilbert-Schmidt scalar product. And we have this initial point in the block wall and this target point on the block sphere. And it's interesting that the optimized trajectory is not simple. I mean that the optimized trajectory does not go directly from this point to this point. We firstly move to the three x3 x, and after that we move to the this pole, and after that we see that the trajectory has this fast moving on the Bloch sphere with some accuracy, of course, because of dissipation. And it's very interesting, and we suggested some decomposition for this optimal control problem in this article, because you see that for example, we can consider separately as a problem of moving on the sphere. And it's important because here we have zero controls, both coherent and incoherent controls zero. Incoherent control is all the time here, but coherent control has this fast gives this fast movings here, and this simple part. In other words, it's very this is an interesting illustration for the importance of analyzing structures of optimized control processes. Another example for the problem of steering with minimizing the finding time, when we have some target point in the Bloch ball, and various initial points on the Bloch sphere, we can consider some training data set obtaining using some optimization methods, and after that for piecewise constant controls, and after that the corresponding regression problem for predicting controls and final time if we have some initial point and it's needed to predict the corresponding control and final time with sufficiently good accuracy. We say about suboptimality, but it's of course it's important that the corresponding accuracy should be not bad, and we see that mean values for the corresponding errors when we consider some additional test points. We see that these mean values are not too bad, and this point corresponds to only 10 points from the training data set, and the total data set contains 200 points, and the corresponding optimization results. I mean, and it's interesting to note that we considered this method neural networks and some regularization for controls, and these not bad results are due to some structure, of course, some structure for the found controls via the applied optimization methods. And after that, I want to say about the importance of using various optimality conditions, some interesting aspects. Following this article, we consider this requirement and Pendragon function and the vector conjugate system and the corresponding transversality condition. Zero controls, coherent and incoherent controls satisfy here to the Pendragon maximum principle as single controls. And after that, we showed that these controls satisfied to the gabas of second order necessary primary condition using this matrix conjugate system, and considering this inequality according to the gabas of theorem. It's important illustration that if we have some controls obtained, for example, from our physical intuition, and we want to check these controls according to optimality condition, so we for example, have possibility to provide all computations only using analytical considerations without numerical methods for differential equations. So some illustration of this aspect and of importance of using optimality conditions, of course. And of course, another way is to consider optimality conditions for sequential improvement of or approximating for controls. The second topic is reachable and controllability sets. These well-known definitions for some given final time, we consider a reachable set for some given initial density matrix, and controllability set and some given target density matrix and final time. We considered various approaches for approximating reachable and controllability sets, and the abstract for my talk contains more references. And here I consider some constructions from this paper. And just for some illustration only. Consider this objective functional, and it's needed to minimize it as this functional, and only 6 cases for this vector A. According to the theory, we can consider the method for approximating convex house for reachable sets, and this case with 6 directions provides us some parallelepipedal estimations, and this slide shows the results for various initial points. This point represents the complete mixed quantum state, and some another point, and we see here sections of these parallelepipedal estimations found by this approach. And it's from physical point of view, it's interesting to say about this picture the following. We see that growth of these estimations, these estimations grow fast when the initial point is not the origin, because as I said before, this point represents the complete mixed quantum state, and of course for purification it's needed more time. Some aspects of numerical optimization. Here we see that the found optimized trajectories have common parts here. Controls and trajectories, I mean, controls and trajectories. And it's important to consider this aspect. In the frames of this approach, for this objective functional, let me consider the problem of minimizing this objective functional and zero coherent and incoherent controls when the final time is from this range. For example, this value. And this control, as it was analytically shown, satisfies the quadratic maximum principle for the general class of piecewise continuous controls. Type of course controls, not problems. And as it was shown numerically here, we see that this control is not optimal. It's some underwater rock for numerical optimization, of course. Some illustration, because in other problems we can consider some similar situations. And this situation is because the quadratic maximum principle is only the necessary condition for optimality, not a sufficient condition. In contrast, for example, to Krotov sufficient optimization, sufficient conditions for optimality, Bellman. And these interesting pictures show us the importance of for adjusting algorithmic parameters for methods. Here we consider the same optimal control problem, but we consider not both zero controls. We consider these initial controls, initial guesses. And here we compare the results of the following method. GPM1 is gradient projection gradient method. One means that this method uses only information from the previous iteration, one-step method. And two means that we consider information from the previous two iterations, a two-step method. This method is the projecting version of the heavy ball method. Also, it's known as a method, suggested by Boris Tyaderovich colleague. And for the projection version for finite dimensional optimization, you can read the article by Antipin Anatoly Sergeyevich, and also another articles about such methods and you will know. I see. I think that you will know that in machine learning, it's important to consider accelerate methods, for example, Nesterov method and so on, various methods. This method is some example for such acceleration for gradient optimization. And these pictures show that we can consider various situations. For example, this situation for the alpha parameter is bad because this situation shows that there is no convergence of the gradient method. And this curve for this adapting of the parameter alpha, alpha parameter is considered for the gradient of the objective functional, and if we consider approximations in the functional space, I mean free share derivative, and also we can consider the corresponding situation when we consider gradient in final optimization, when we these gradients are connected, of course, when we consider piecewise constant controls. And this curve shows that we have good convergence of the method. And this curve shows that for the same adaptation of the alpha parameter, we have a better convergence with help of not a complex additional term of the second case, I mean two-step method. And this parameter is used in this additional term. You can see about the Pollock favorable method and about another such methods. And the first order growth method with some regularization is also very good when we adjust the regularization parameter correctly. This slide shows the importance of such adjustments for the parameters. And about various kinds of the Croto method for various optimal control problems, you can see our survey, this link 7. This link in the Russian Mathematical Survey, успехи математических наук, journal. And this slide shows our conclusions. We consider open quantum systems whose dynamics depends on coherent and incoherent controls. It's important because we can combine possibilities of both types of controls and use together these possibilities. But the current talk is mainly devoted only to the one-qubit case. You can see more references in our abstract. Various optimal control problems were studied by us, including generation of a target density matrix, this Turing problem, Also maximization of various another type, various objective function of another types. Various classes of control functions can be used, and various optimality conditions, optimization methods, also machine learning can be used also. And about the found results. First, we analyzed the structures of the optimized control processes for various classes of control problems, for looking for various patterns, interesting situations. I could this interesting example shows interesting situation for decomposition. It's very important for optimization. And the second item, various situations were analyzed. For example, a single control satisfying the gabas of second order necessary condition for optimality. Also, non-optimal controls satisfying the Pendragon maximum principle. It's a very important aspect for optimization from the optimization theory. Various nuances for adjusting parameters also were studied by us for various optimization methods. And also nuances for geometry of reachable and controllability sets under various conditions for controls and